Hello, Jürgen. Thank you for joining. Jürgen is our expert on battery, and battery, of course, are nowadays key components of the automotive industry, responsible for performance, driving range, durability. So, of course, we also have a strong focus on this topic. And I'm curious, Jürgen, is there anything new from your side in this release?
Yeah, hello. Definitely, as you said, battery is extremely important now, and it's also for us extremely important that we put a huge focus this year on the battery, and I'm super happy with all the features that have been brought into the new release. It's just a huge list, and just to cluster them, we just listened to the customers, and we heard most of the time it's about speed, getting faster, doing things in shorter time, reducing testing effort, and simulation is here definitely a key requirement. And on the other side, of course, also more going into physics, more electrochemical models, and so on. So therefore, just those two, let's say, groups I would like to focus today. So let's first have a look at the speed, as we call it, capabilities. So we really took a boost here in our workflow, where we're just looking compared to what we did last year with the release, a massive speed up. So compared to the pre-processing time, the solver setup and running, but also, of course, the post-processing, we just see that the new release brings up to 10 times faster pre-processing, up to 5 times faster in the solver run. And of course, also a massive improvement on the post-processing. And in order to show those things in detail, I brought my colleague Gernot with me, and he just can show us a little bit a sneak peek what is new there in this new release on the pre-processing.
Thanks, Jürgen, for having me. Also, thanks, Oliver. I'm happy to present to you some new features that we have here, FameM-Flex. In a nutshell, FameM-Flex is really a game changer on how we approach pre-processing. And I would like to demonstrate that to you in a simple example that we have here. So this is just a battery module with some cooling domain on the bottom and with some battery cells that act as our heat sources. Now, up to now, we were mainly used to a conform meshing approach, which means that if we cut into the mesh, for example, we will see that all the connections inside this mesh are node conformal. What does that mean? It means that numerically it's a very precise way to approach these things, but the meshing takes quite some time because everything needs to be meshed in one process, more or less. With FameM-Flex, we changed that a little bit, and let me show you how that works. In principle, it's always split up into 3 steps. We load our geometry, or we define our geometry. We define which meshes we want to use. In this case, we want to combine a poly meshing with hex meshing. We then assign which meshes should be applied, and then we define how the interfaces should look like, more or less. So what is the benefit now of that? It's more or less twofold. First of all, we are able to combine different meshing types, which is quite convenient depending on the application. And with that comes also that we are able to run parallel meshing. And this is what Jürgen mentioned before, which allows us to really cut the meshing times tenfold. So on a conform battery pack geometry with 230 million cells, we were able to cut the times from 15 hours to 2 hours. So really considerable. And even 20 hours when we started even with that. So this is one thing. As said, it's a game changer from my point of view. But this is not the end. We are basically able to do even more things with that. So you might imagine you have this battery module I showed to you before. We have a cooling domain that looks like that. But what happens if you receive another geometry from your design department? Maybe something that looks more like this, just a different domain here. In the past, this always required us to remesh the entire geometry, but with FameM-Flex, we are now able to just reuse parts from an existing mesh and remesh only what is needed. And this is something that I can actually demonstrate live. So in that case, we just create a new FameM-Flex. We load our new geometry with the changed cooling channel layout. the edges for that. We then add measure settings, so we are just copying from an existing set of settings, which is also easily possible. We then add an existing volume that we define, so it's in this case already loaded here, and then we perform 2 assignments where we say, okay, which parts of the geometry should be meshed how. In this case, we start with the poly measure, which should, we should mesh 2 domains out of the 10 or 20 that we have on this geometry. And all the other ones should be taken from the existing volume that we have. The interfaces we leave like it is. And now we simply say, please create this mesh. And since only a small part of the geometry needs to be remeshed, we should be able to see a result quite fast. So running through the measure. And now it's done. And let me just show you the entire geometry. Oh, sorry. This is how our end result looks like. And we basically reused all of the top parts of the previous mesh. So here you can see it. The cooling inlets and outlets changed, but everything else remained the same. As you can see, for example, for these grid lines, they don't change. That means the mesh is the same. Yeah, this brings me to the end of my short presentation. Of course, I could talk even more about that, but I guess it's better to hand over to you, Jürgen.
Yeah,
thanks.
Cool.
Yes, thanks a lot, Gernot. This was really impressive what this means on improving the speed of meshing, the speed of turnaround time doing such a project. We concentrated now a lot on speed up and productivity enhancement. But development technology and battery technologies is developing rather fast, and I assume there are also updates on the technological side. So what can you tell us here on this aspect?
So as you can also see, we had a lot of features, and development focus was also on electrochemical modeling, because also here the market has a strong demand, going more to physicality, and to be able to look inside the battery cell to understand all the mechanism for aging, the mechanism for fast charging, and so on. And therefore, we also put here a dedicated focus on one of the main pains that customers currently have, is how to parameterize the electrochemical model, because that's the door opener for a completely, let's say, new way of simulating cells. But if you don't have the skills to parameterize, it's just closed. And therefore, with the focus on the last release, but also with this release, we introduce new wizards that help the user to do the parameterization of an electrochemical model really easily. And I also have brought a colleague, Christoph, with me just to show what that means in this particular case.
Thanks for having me, Jürgen. Today, I want to show you the latest addition to our wizards, namely the electrode balancing wizard, and I have prepared a project which demonstrates how to use it. So I'm going to start it by going to the efficiency portal, and here you can already see the electrode balancing wizard with some description, what is necessary to be done, and I'll jump straight to it and click on start. First, you start on a landing page where you in principle can define if you want to do this parameterization process for a cathode, anode, or for both together. You also have several options here which are suitable to your specific use cases, but I'm going to show you just the basic setup to help you getting an idea. I click on next, and first step is basically already the most necessary, the basic one. You need to somehow get your measurement, which is OC circuit potential versus some charge, to your simulation state, here the stoichiometric coefficient. And this page is clustered into 3 parts. The first part here is some basic input data which you can get, for example, from teardowns, which are anyway necessary to do this parameterization. The second part down here is the input, so basically measurement of charge versus open circuit voltage. And on the right side, you first of all see your data. That would be here the topmost picture. Then you see the derivative, which is suitable for some specific setting. And down below, you see your result, where you basically see the open circuit voltage plotted against the stoichiometric coefficient. And this is the first step. So you need to put this in, and then you get your data, which is necessary to run the model. Once you have done that and you're satisfied with this result, you can click on next, and you go to the second step, which is also important because it is for when you set up a full cell model, which in the end is what we want to do. We want to have a performance model for a specific chemistry, which has a cathode and the anode. You have to find out where the corresponding stoichiometries are for SOC0 and 100 in your cathode and also in your anode. And for this step, basically you can do again, you need to do a specific measurement in a 3-electrode setup. For example, in the documentation, we show exactly what needs to be done. And you also need some basic input like the capacity and the electrode area. And then you fit basically your curve, which you get from the previous step, and your measurement curve. And you see here the result, your stoichiometries corresponding to SOC0 and SOC1. If you're satisfied with that, you can click again on next, and you see already you're done. You see a summary slide where you see all the input data which you generated, clustered into different parts. And on the right, you see your final open circuit potential curve. You can also set how you want to interpolate it. And if you're satisfied with that, you simply click on finish. Once you're finished, the good thing is that you already have your material loaded. So here you see already it's called Electrode Balancing Wizard, cathode 1. So you already have this information stored in your battery. And I'd like to jump to the property database to show you the main benefit of this approach. Because the good thing is that you don't really generate this only for your electrochemical battery, but you really generate a new input in your property database, which you can also use for other batteries. So you see you have all the generated inputs already filled out. For example, in the open circuit potential, if I scroll down here, you see that exactly the curve which you generated is now inside this table. And with that, basically, you can, at the end, already simulate an open circuit voltage for a specific measured electrochemical battery cell. This is all which I wanted to show. I just wanted to show you a short glimpse, and I'd like to get back to you, Jürgen.
Thank you, Christoph.
Yeah, really, really impressive. I learn a lot from engineers that they are concerned setting up electrochemical battery models because they worry that they are not able to enter the proper data and set up the model. But now with the new Cruise M version, it seems that it's really a good guidance for the engineer to set up such models and to parameterize them. It's a great door opener for them.
Exactly. Yeah.
When they now have electrochemical battery models, what does it mean? What real advantage do they have against equivalent circuit models? For what purpose can they use it now?
I mean, what we see is there's a lot of interest to understand better what happens inside the cell, what causes aging, what, let's say, are the limiters for doing even fast charging in shorter time. And in order to do that, you need physical models to understand the processes. And now with these parameterized models, you can really understand much better those drivers, those limiters, and develop proper fast charging profiles, but also, of course, reduce the aging or the mechanism that mainly damage the cell over lifetime. And especially also, it would now open the possibility to do, let's say, the BMS calibration with an alternative approach. So far, you always need testing the data, the pulses to do the RC model creation based on test data. Now, for example, also with an electrochemical model, you can virtualize this process, doing these pulses with an electrochemical model, and also significantly reduce the effort and the time for creating these BMS data for a new cell or also for an aged cell.
So that means productivity enhancement does not just mean making simulation work faster, modeling faster, but also to replace classical testing tasks with virtualization, with simulation, to also be more productive and do cost saving. Is this my right understanding?
Exactly.
Yeah?
And then again, I come back to the first part of speed, yeah, because at the end of the day, simulation is significantly faster than real time. So you also can do the testing in a, let's say, significant shorter amount of time. So yes, your conclusion is totally right.
Yeah, then thanks a lot for presenting this wide range of new things, and it's just up to our users to step into these new things, install the new version, and get used of this wide range of new features. Thank you.
Thank you.